Thanks. Hey, guys. So my name is Naveen. I'm from LinkedIn. I work for the data infrastructure team at LinkedIn. I'm going to talk about Samza, which is the stream processing framework we have at LinkedIn. So this is the outline of the talk. So I'll explain what's stream processing and why we use Samza at LinkedIn, how it's architected, and in this section, I'll also be talking about where we use RocksDB in Samza. And since we're an open source project, we have pointers for you to contact us for contributions or help, etc. Cool. So I guess I'll get my notes. Okay. Stream processing. So what is the need and why and what is the need for stream processing? Oh, it's over there. Okay. All right. So you have two types of, typically in any internet company, you'd see like two types of processing that you would need. One is kind of like RPC, where when a request hits a web page, you have a bunch of service calls that go to the backend, which is typically synchronous RPC calls. Or the other hand, you would have a batch processing framework, which is done much later, like in Hadoop or some stuff like that. Somewhere in the middle is where Samza is, or stream processing is, I should say, where a latency of milliseconds to minutes is acceptable. So typically, the data for streams are from streams publisher subscriber systems like Samza, Kafka, RabbitMQ, ZeroMQ, etc. At LinkedIn, we use Kafka, and we heavily use Kafka, in fact. So once you start processing these events from stream processing from streams, you would start noticing that there's a common set of problems that you would have to encounter or you have to solve. For instance, I highlighted some of them. For instance, partitioning. The stream itself might be partitioned, and the output of the stream is also partitioned. How are you going to deal with that? State. What is the state of the web service that you're writing between messages that are being processed? Reprocessing. If the algorithm of your web service changes, how are you going to recompute the whole stream with maintaining consistency? Failure semantics. If your job fails, how are you going to spawn it again? There's another pattern where you would do joins with streams or other services or other databases from streams. So non-determinism is a very important aspect of it. So by that, what I mean is if the stream fails and your processing fails and you want to go back in time and do the reprocessing again, then you might have external systems that you query which are time-dependent, and ordering might matter, et cetera, et cetera. So Samza tries to solve all these problems, and so henceforth is a stream processing framework. The primary component for messaging is Kafka, although that's pluggable in Samza, but by default it ships with Kafka. And we use Yarn, as many of you might know. It's an artifact of Hadoop 2.0, which provides fault tolerance, process isolation, security, resource management, etc. Okay, so I will go over an example use case that we have Samza deployed at LinkedIn. So when you go to the LinkedIn webpage, as you can see, when you go to the webpage, it makes a bunch of service calls to different other services, which might call another services. So henceforth, there is a tree of services that are called, as you see at the bottom. This tree is of interest for us because we would like to see what latency each service takes and to zero on and improve performance on certain services. So how we construct this tree is done, we do it through streams. So each service, when it processes a request, sends a message to Kafka saying that, hey, I processed this message which is keyed on page ID. What page ID is a page from which the request is originating. For instance, it could be from home page, or it could be from jobs page. It could be from various pages. But what we want to see is a tree for a particular user. So when the user hits the LinkedIn web page, we assign him something called a tree ID, which is unique to the user. So the first series of Samza jobs that you see, what they essentially do is repartitioning, which if you worked in Hadoop, you can imagine it to be something similar to Mapper, where you are reassigning the event itself to a different ID, which is the tree ID. And in the second step, what it does is it's another series of Samza jobs. What they do is aggregate all these tree IDs, and henceforth, you can construct this graph you see at the bottom. So this is a very famous example that we used in LinkedIn. It was one of the first use cases we used Samza for. So I'll go over some of the concepts and architecture of how Samza is designed, and what are the assumptions that we make. So as I said, so in LinkedIn we use Kafka, which is a partition stream. So anytime you publish a message to the Kafka for any particular topic, it's partitioned essentially. So it can have 64 partitions, 128 partitions. The message goes depending upon the partitioning scheme you use to the corresponding partition. So in Samza, what you have is a basic unit of processing. It's called a task. What it does is it gets a message from a partition and then processes it. We have a very simple interface that you'll have to implement. Say in this example, it's called a stream task, and you have a process callback for each message. The envelope itself contains the message, and then there's a collector which outputs the message to a different stream, and then there's a task coordinator where you could manage the life cycle of the task itself. So this does a very simple computation of getting the message, getting the page key, and then incrementing the page count, and then it sends it to a different output stream, the page key. So it's essentially counting the number of times the page has been viewed. This is the same example of the previous thing. So as you can see, it's processing, outputting to one partition, processing, outputting to different partition now. And it checkpoints. This is taken care of by Samza. So it's essentially marking that I've processed 2 messages now so far from this particular stream. So job is a higher level view of what we call in Samza is a collection of tasks. A task, as I mentioned before, is just an instance of a code, and a job is a collection of tasks which compute different partitions from Kafka. So you can do stuff like join different streams and output to a different stream. As you can see here, it's joining stream A and B and sending the output to stream C. An example of this would be so ad views. So if a user views an ad, if you display a user an ad and then the user clicks the ad, you have 2 streams. One is the ad views and the ad clicks. You can do a join on these 2 streams and get the click-through rate of the ads, essentially how many times that ad has been clicked. This is a more real-world deployment of how Samza is deployed. As you can see, I'll simplify this. This also shows the partitioning, but this is the most simplified view of the same thing. So you can see job 1 and job 2 are outputting to stream E, which is consumed by job 3. One thing I'd like to point out here is that if job 3 goes down, it does not affect job 1 or job 2. The output is still sent to stream E, which is a Kafka topic, which would keep accumulating data, which is a distributed queue itself. When job 3 comes back, it no longer has dependency on job 1 or job 2. It just starts processing from where it left off in stream E. In fact, you can spawn a new job 4, and process stream E without disturbing other jobs. As I said, we use Yarn for several things. I don't want to get into the details, but a high-level overview is we do resource management with Yarn, meaning that you can say, give me a machine with 1 gigs of memory to run this job. If one job is misbehaving, move it to a different machine. If a job fails, then spawn it in a different machine, etc. So this is where I think it's relevant part where we use RocksDB in Samza. So Samza itself doesn't have SQL, but I'm using this as an example to show what kind of operations are usually performed on streams. For instance, this does a projection on column 1 from stream 1, a count on the same column, and a group by join of streams or streams with other databases. A slightly complicated example where you would order by, which would mean that you would have to buffer, and you can use these kind of operations for calculating, give me the top 5 shares in the past n minutes, or stuff like that. So for stream processing, meaning that, for any of these operations that we discussed here, we would need to have the data buffered somewhere. So how do people do it without Samza or any other stream processing framework for that matter is most people query an external key value store. And this is a remote call, and it's quite expensive. I'll explain why. So streams are typically much more faster than DB operations because of different data consistency guarantees the database provides compared to streams. So what happens is if you are going to query at the same speed, then the database is going to be affected for other traffics, which are serving online traffic, say. Mutations is, let's say you're processing a stream and your stream crashes and you're trying to go back and reprocess again. there is no guarantee that the remote store, the key value store, is not mutated because there are multiple people accessing it. So there is no guarantee that the state is going to be consistent. So here's actually an example from, I think this is from Voldemort. Yeah, so if you look at this, at around 17, so till 17 hours, both the store is serving both real-time traffic and traffic from a stream processor. It's around 17 hours. The stream processor goes down for maintenance failure, whatever reason it might be. At around 6 p.m., it comes back again, and it has backlogged so many messages that when it comes back up, it is pounding the database with so many requests that it's actually affecting the database. If you're operating an internet service, this is not something that you want to do. So the way we tackle this with Samza is we have the storage itself embedded as a part of the task, and this is where we started off using with LevelDB, and we have support for both LevelDB and RocksDB now, and this is where RocksDB comes into picture. So the way we do this is any write that goes to any buffering that you might have to do with the task, a write goes to RocksDB or the storage, and another write goes to Kafka, which we also use as changelog stream. So any write you make to the task 1, for instance, now goes to the RocksDB, and then another write goes to partition 0 of Kafka. Likewise for partition 3 and partition 2. If the task itself goes down, then we restore the state, the RocksDB store from Kafka. So we have a very simple pluggable API, put, get, deletes, range. All of this is implemented. We have an implementation of this in RocksDB, which is the default implementation. Here are some patterns that we use from Samza with and access the storage engine essentially. So for caching, we do a bunch of writes and then read the data from it later on. Like I said, the page count example that I showed you, so it should essentially just to count the number of times a page has been viewed. It does a bunch of reads, writes, reads, writes. Join, and 2 streams are joined, you would want to wait till you get a particular event, and then once the join's performed, then you delete it. So it's going to be read, write, delete, read, write, delete. Batching is something very similar where you accumulate data, and then after some time, you are going to write it to a remote machine. And materialized view is also very similar to that, where you can construct a materialized view from the stream. So one thing to point out is that every task in Samza is single thread. So we have only 1 thread and 1 compaction thread. So all these numbers that you're seeing should be associated with that when you look at this. The average row size for us when we performed these experiments were about 1 kilobyte. So we got about sequential writes and random writes about 40,000 QPS. We also varied the write buffer in RocksDB to see how it performs. And but at about 100 MB or 150 MB, we hit the sweet spot where we got about like 40,000 QPS, which was sufficient for a use case. The bottleneck was actually not from I/O, but we found that the bottleneck was from the CPU. It was waiting on I/O wait and hogging up about 95% of the CPU. What else? Yeah, so we have random reads, which was around 28,000 QPS, and restore throughput, which is, as I said, when the store fails, we restore from Kafka, and we're able to get about from 20,000 to 25,000 or 26,000. That's about it. So we are an open source project, so if anybody wants to contribute or use it, we have some useful links here, so feel free to go crazy. All right. Oh, for Q&A, I think we'll do it after Ankit finishes talking, depending upon how much time we have. Thanks.
Hello. Okay. So my name is Ankit, and I'm a software engineer working at LinkedIn. I'll be giving an overview of FollowFeed system, which is the backend system powering all feed applications at LinkedIn. And also I'll be giving an overview of how RocksDB is used inside this FollowFeed system. As most of you in this room might already know, a feed is a constantly updating list of updates and content that are personalized to the viewer. Let's take an example. This is the homepage feed, where you see updates and content from your connections, which is then personalized to the viewer using some relevance algorithms. So there are many ways to solve this feed problem. FollowFeed takes the approach by building an index called a timeline. A timeline is a chronologically ordered list of updates by or about an entity, where an entity can be a member, school, company, or group. Some examples: by use case, member shares an article. This is an update by a member, that's why it goes in his timeline. About use case, member is mentioned in an article. It's about the member and it goes in his timeline. This timeline data is then stored inside the timeline storage cluster, which is sharded into M replicas, where sharding is done using the timeline entity ID, and the data is then replicated into N replicas. Data is ingested into these N replicas using Kafka, which is a pub subsystem, as Naveen already explained, and is open sourced by LinkedIn and is a top level Apache project. The beauty of this architecture is that each replica just subscribes to the Kafka channel on its own and ingests the data at its own pace. So if I want to add a new box or a new replica to this architecture, it's as easy as spinning up a new box or a replica. It will automatically subscribe to Kafka and will start ingesting data. It's as simple as that. Now, if I have this timeline data, how do I create feed from that? Let's again take an example. Let's say we want to render feed for person 1, which is connected to persons 2, 3, 4, and 5. We have the timeline storage cluster in which we have two boxes. One box containing data for person 2 and 3, the other one containing data for 4 and 5. Feed request comes for person 1. Query service talks to some downstream service to find out the list of connections for person 1. This downstream service returns the list of connections, in this case 2, 3, 4, and 5. Then query service talks to the timeline storage cluster to find out updates for these persons 2, 3, 4, and 5. In this case, query service goes to box 1 to get updates for 2 and 3, and goes to box 2 to get updates for 4 and 5. Each timeline storage box then gets timelines for all these persons, blends these timelines, applies filtering and relevance algorithms on top of them, picks top N updates from them, and returns them back to the query service. Query service then merges these lists of updates coming back from the timeline storage cluster, applies relevance algorithms, and returns top K updates back to the viewer. In this example which we took, we were concentrating more on the persons or on the connections. But FollowFeed is more generic than that. FollowFeed, we can compose feed using timelines of any entities. To define it more better, FollowFeed serves relevant updates to viewer from entities to which viewer has a relationship represented by an edge between a viewer and entity in the connection graph. In a previous example, we had person 1 connected to 2, 3, 4, and 5. In the terms of this definition, person 1 had the connect edge with 2, 3, 4, and 5 in the connection graph. And that's why FollowFeed was able to serve the updates back. But as I said before, it is more generic than that. So FollowFeed can serve back updates for company, school, or other such entities, and it can serve updates from entities which have other edges like follow edge. Now I will take a deep dive inside the timeline database and how we store this timeline data inside. So data for a particular timeline is stored into multiple blobs. Taking again the example of person 1. So person 1's data is stored in n blobs, and the keys for these blobs are person 1 underscore n corresponding to blob n, person 1 underscore n minus 1 corresponding to blob n minus 1, and so forth. Blobs over here are just byte arrays. All the blobs in this timeline are reverse chronologically sorted. So blob n will have updates which are more latest compared to updates in blob n minus 1. And updates in a particular blob are also again reverse chronologically sorted. So updates at the front of the blob will be more latest compared to updates at the end of the blob. And at the end of the blob, we then store the key for the next blob in the chain, which gives the whole timeline a chain-like structure. It allows us to traverse the whole timeline easily and to get the data for the whole timeline by just following the next pointer. Now, somebody can ask that, why do split the data into multiple blobs? Why not just store it into one big blob? Well, as this is a time series data, the most common query which we will see for this particular data set is get me the updates for a particular time range. Now, for such queries, it makes sense to split the data into multiple blobs because you just read those blobs which satisfy your time range query and then just get only those blobs from the database. You don't have to get rest of the other blobs for the timeline from the database. To facilitate such queries further, we store metadata information about the timelines in a separate key. So, again, the example of person 1, for person 1's timeline, we will have a key called person1_metadata, which will store the list of metadata information about all of the blobs of this timeline. Each metadata information of each blob contains timestamp of latest update in the blob, timestamp of earliest update in the blob, and the number of updates in the blob. Now, if we have a time range query coming for a timeline, then we just read the metadata information. We find the blobs which satisfy this time range request and then read the blobs from the database. So this metadata can be used now for pruning of data also. So when we get a write request for a timeline, just read the metadata information, see if any blobs or updates need to be pruned based on retention policy, and just delete them from the database. Now this is a stateful system. You have to take backups. So in this, for taking backups, we have one replica just dedicated for backups. This replica gets write requests, but it does not serve any read requests. And the only purpose of this replica is to take incremental backups after every X hours. So now I will change the direction of this talk and I will discuss how and why we are using RocksDB in FollowFeed system. As I discussed before, each timeline storage box runs relevance algorithms. And the major requirement of these algorithms is that they require a lot of data to serve good recommendations. Now, if we don't use embedded databases, then we will have to go over the wire to get a list of these large, a list of this large number of updates. And it can be quite costly in the terms of read-side latency. So we need an embedded database for this architecture. And we chose RocksDB because of these reasons. Merge operator support was available in RocksDB, and it allows our application to support write-heavy use cases in future. And as RocksDB team has put it in the previous slides that, yes, it is fast. So we evaluated the performance compared to other databases, and we found out that it was really fast for our use case. And we chose to use RocksDB then for the FollowFeed system. Deep diving into the RocksDB usage, FollowFeed is a Java application, and we are interfacing to RocksDB via RocksJava. We are using multi-get, put, delete, and incremental backup operations from RocksDB, and we use universal compaction, Bloom filter, and block cache. Regarding performance, each timeline storage box contains approximately 1 billion keys, and the value size is from 500 bytes to 1 kilobyte. And we are able to get approximately 500 writes per second and 100,000 reads per second with 2.9 percentile latency of 1 millisecond for write operations and 2.9 percentile latency of 2 milliseconds for read operations. Last but not the least, RocksDB experience. For us, RocksDB has been really solid as far as performance is concerned. GitHub support is awesome. Thanks to you guys. The turnaround time on issues and merge requests is very minimal, which is great. The negative things which we found from RocksDB, not the negative things, but things which can be improved upon. First thing, tuning. I think this has been really nailed down in this meetup today by RocksDB team that yes, they are working hard on this. And I think this is very essential so that new users can easily adopt RocksDB. And also, transactional support, if it is available by RocksDB, then it will be really useful. For our application, for every write operation, we had to mutate multiple keys. For example, I gave the metadata key and the timeline block key, and they have to be consistent with each other. Without the transactional support, we had to build redo dogs ourselves, and it would have been great if RocksDB natively supported the transactional support. Just a request, but no big deal. And that's all from me, guys. Thank you. Yeah, if there are any questions, guys, then, and also Naveen, if he wants to be there, yeah.
Hi, my name is Rashid. Thanks for the talk. It was really awesome.
Thanks.
With regards to the numbers, are these including data feeding in cache or data overflowing on the disk?
So this was, I think slides were taken off. So this was directly from RocksDB, but we were using block cache. I don't exactly remember if we were using disk or not, but the numbers which I gave you were for the benchmarking, and at that time IOStat was reporting 100% utilization. So I was maxing out the SSD card at that time. Yep.
So why do you use universal compaction?
Why was I using universal compaction? That's a good question. For this particular application, we are using read update writes, and where the level compaction, we were using a lot of high read amplification and write amplification. And because of that, we were not able to support a lot of writes per second. With universal compaction, the read amplification and write amplification went to less than 1. And it became very easy to support a lot of writes per second.
So do you happen to use Helix for cluster management?
No, we are not using Helix for cluster management. As I said before in the slide, or maybe I did not mention it, all the replicas are master-master, and all of the replicas are serving read requests. So Helix is mostly used for master-slave architecture, that if a particular master goes down, then you have to do a handover, and it's mostly used for those purposes. So right now, there is no need to use Helix, but as this is a cluster, we can try to see if we want to use Helix in the future. Yeah.
When you mentioned desiring transaction support, do you mean by that MVCC or rollback? Or
Rollback features,
Okay.
mainly. Because if one particular put passes or one particular mutation passes and the other one fails, we have to make sure that the other one is also rolled back. So mainly the rollback operations.
So did you try using some of the other SSD formats that are available in RocksDB, things like plain table SSD format?
No, we did not. We benchmarked just with the block table format, and we have not tried plain table formats. We did not benchmark them. Yes?
What other databases did you consider?
We tried BerkeleyDB because it was used in LinkedIn previously, so we had expertise of BerkeleyDB. With BerkeleyDB, we were not able to get good performance. The performance which we wanted for this application, mostly it is a read, update, write on the right use case. And with RocksDB, we were able to get, I don't remember the exact numbers, but it was orders of magnitude compared to BerkeleyDB. Cool. Thank you, guys.